So last time we got to talking about E1 and E2 eliminations, and we recognized that there are some similarities between E2 and what else, other reaction? SN2. And what are the similarities? One step. What else? Second order. Okay. What else? Not an E2, right? Because it's one step. What are some of the differences? Well, yeah. Right. So in one case, in SN2, where the Lewis base is functioning as a nucleophile, in an E2, the Lewis base is functioning as a base, right? E2 likes tertiary carbons. Well, you can't have the SN2 process. So yeah, I mean, it does. We see that works because we're doing what kind of elimination? What do we call it? It was a Greek letter. Beta elimination. That's right. Right? So the alpha carbon's where the halogen is. We just determined that leaving group matters, right? We know that alkyl fluorides essentially are unreactive. Alkyl chlorides are faster than alkyl fluorides, alkyl bromides, followed by alkyl iodides, right? So as we go down the family, the leaving group improves, and we just demonstrated that through an SN1 reaction, right? We know that the bromide reaction went a whole lot faster than the chloride reaction by quite a bit, right? Imagine what it would have been like if we had tried to compare bromide versus iodide. Why did I not pick bromide and iodide? Because by the time I added the alkyl iodide, it would have almost immediately changed. It would have been very difficult for you to get a good time on it. So I picked an alkyl chloride and an alkyl bromide. Okay, we had something we can measure. I didn't pick alkyl fluorides because we'd still be waiting. And you'd be waiting tomorrow, and you'd be waiting the next day, and you don't have enough memory for that for sure. Okay, so E2 eliminations are going to follow the leaving group trend. So the better the leaving group, the faster the reaction. And polar aprotic solvents increase the rate of E2 reactions, just like they increase the rate of SN2 reactions. So there's a lot of relationships between SN2 and E2. Okay? The difference is the product that you get. In an SN2 reaction, you're going to get a substitution product. So whatever the nucleophile is, that's what's going to be on your organic molecule. In an E2 reaction, you're going to get an alkene. Now, it turns out that E2 reactions follow a little different trend than SN2 in terms of the type of alkyl halide, whether it's primary, secondary, or tertiary. And it turns out, as you know, that SN2 reactions favor primary alkyl halides. Secondary is okay, tertiary, no SN2 chemistry, right? It's exactly the opposite for the E2 reaction, okay? In the E2 reaction, tertiary alkyl halides actually react very, very quickly, whereas primary alkyl halides are much slower to eliminate, okay? And it has to do with the fact that a tertiary alkyl halide, is that bond between carbon and bromine stronger or weaker? It is weaker. Now tell me why it's weaker.
Because there's less of a polar charge there. You got the other carbons, you can kind of balance out that charge over.
Okay, you're on the right track. So if we think about what it makes a bond weak. Stretching, okay? So the length of the bond, right? Weak bonds are going to have long bond lengths, and stronger bonds are going to be shorter, right? So if you actually did some calculations and looked at it, what you'd find is that a primary carbon halide bond is actually a little bit shorter than a tertiary carbon halide bond, okay? Meaning that this bond is a little weaker. And the reason is because as we stretch it, this takes on a partial negative charge, right? and this takes on a partial positive charge. Just like here, we have a partial negative and a partial positive. But which one of these partial positives is more stable? This one, because the more alkyl groups we have, we know that that stabilizes a carbocation. This isn't a carbocation yet, but it's starting to look like one, right? And so that's why we see the trend that we see, okay? Also, the base in an E2 reaction doesn't actually attack the carbon, right? So is there as much steric hindrance to take into account? No. The SN2 reaction follows this trend because the nucleophile actually has to attack the carbon. And the more stuff that you have around that carbon, the slower it's going to go, right? So if we look at a primary alkyl halide, right, the OH group, in this case is what we're going to use as a base, comes in, abstracts that hydrogen. These electrons form the pi bond, and the bromine leaves all in one step. And we end up with a monosubstituted alkene, right, which is less stable. And that goes through the transition state. This bond is actually a little stronger, if you will. Okay, so if I look at this, how is the base coming in and the leaving group leaving? How is that arranged? From the back. Okay, so the hydrogen and the halogen have to be how to one another? Kind of trans to one another. That's right. So it's not this hydrogen that does the chemistry. It's this hydrogen that is trans. Now in a tertiary alkyl halide, the same mechanism is happening. Notice the nucleophile, or the base, is not functioning as a nucleophile, so there's really not any steric hindrance involved with the base approaching the hydrogen. These electrons come in or form the pi bond, and the leaving group leaves, and we end up with the more stable alkene. And so that's going to lower that transition state, right? And so that's why we see the trend that we see. So we're going to continue to talk about E2 elimination. We're going to talk about E1 elimination as well. We're going to talk about some of the stereochemistry of elimination reactions, but we're also going to talk about this thing called Zaitsev's rule. It is a rule you need to commit to memory. Okay? And again, I don't say that often, but when I do, it is something you need to commit to memory. Now, you will find Zaitsev spelt two different ways. I spell it with the Z, but you can also find it spelled S-A-Y whatever else, okay? It's the same rule. There's just two different spellings for the gentleman's name. I don't know why, okay? So if we look at an E2 mechanism, right, we can take an alkyl halide. In this case, we're taking an alkyl, or secondary alkyl bromide. We're reacting it with a base. In this case, we're just using triethylamine as a base. It works out pretty well here. We eliminate through a beta elimination, and we get cyclohexene out of the reaction. There are certain characteristics of an E2 mechanism, and we've already talked about a lot of these. The kinetics are second order, meaning that if Gabriella came to the lab and she wanted the reaction to get over twice as fast, what would she do? She would double something, right? What would she double? She could double the base. That would be perfectly fine if she had enough base to do that. Or she could double the alkyl halide, right? And if she wanted it to go a lot quicker, she would double both, and she'd be done in time for lunch, and off she'd go, right? The mechanism is one step. We know that the identity of the R group matters. We know that the tertiary alkyl halides react much faster than secondary, much faster than primary. We know that the base is important. It's favored by strong bases. Okay? We know that the leaving group matters. The better the leaving group, the faster the reaction. And we know that it's going to be favored by polar aprotic solvents. This is how we know that it's going to likely be an E2 reaction versus an SN2 reaction. What key here tells me that this reaction is going to be E2 versus SN2? That's right. And we know that that's exactly the opposite for SN2, right? So that's exactly right. Everything else is pretty much so in line with an SN2 mechanism, okay? Any questions about that? There's one thing up here that's also not mentioned. That's heat. If you want to push something, if you've got a secondary alkyl halide and you want it to do SN2 chemistry, keep it cold. Room temperature below. If you have a secondary alkyl halide and you want it to do elimination chemistry, heat it up above room temperature. So heat almost always favors elimination over substitution. Okay? when you're trying to make a distinction. Rank the following in order of increasing E2 reactivity. Least reactive to most reactive. Which one's going to be the least reactive? Primary alkyl chloride, right. What's going to be the next most reactive? The secondary alkyl chloride, and then of course this is going to be the most reactive, right? Okay. So we're going to have situations where we can rank these based on what type of alkyl halide we have. Okay. There are several reactions where this very simple thing that we teach you as sophomores has been useful for a variety of purposes. So for example, here we have what kind of alkyl halide? That's a primary alkyl halide. And they're going to eliminate to get this alkene. Okay? Why did they pick to use potassium tert-butoxide? Why did they not use sodium hydroxide or sodium methoxide? Yeah, you both are saying the right thing. Right. So we know that this is a strong base, but it's a poor nucleophile. This is a primary alkyl halide. If we had used any other base, we would have had a problem with elimination and SN2 competing with one another, right? And they wanted this to go to complete elimination. So you use a non-nucleophilic base that shuts down the the SN2 pathway. What kind of solvent are we using? DMSO, which is polar aprotic. That's right. This is a polar aprotic solvent. All that's going to favor E2 elimination. You get the carbon-carbon double bond right where you want it. And then they took this molecule and through several steps made quinine. Quinine is an antimalarial drug. And so the synthesis of quinine is actually quite important, especially in areas where malaria is quite prevalent. Yes?
Would they need to heat that up, being they've already kind of got a lot of other stuff going for it?
If it were me, I would have heated it up just to make the reaction go a little faster. But there's no way you're going to get SN2 chemistry to go here. So theoretically, no, they don't have to heat this one up to force the elimination to occur. Here we have what kind of alkyl halide? Primary, and it's a iodide, so it's going to eliminate pretty readily, right? It's got a good leaving group. What's DBU? All right, yeah, so it's the ring, 2 rings, right, with 2 nitrogens. Which nitrogen serves as the base? The sp2 hybridized or the sp3 hybridized nitrogen? It is the sp2 hybridized nitrogen. And if you draw the resonance structures, you'll see why. Because that nitrogen can actually have a formal negative charge on it in one of the resonance structures. So that was one of your assignments to look at for today, was to figure out which nitrogen of DBU reacts. So if you predicted the wrong one, go back and look at the resonance structures. So you've got that nitrogen with the lone pair, single bond to a carbon, which was double bound to the other nitrogen with the lone pair. Draw the resonance structure between those 3 atoms, and you'll see that it's the sp2 hybridized nitrogen that can bear a formal negative charge in one of the resonance structures. Okay? So they got this alkene, and then through several steps we're actually able to make estradiol, which is the female sex hormone. And this is an important synthesis, especially for on your way to like birth control medications. So they will take this and then derivatize it further to make a variety of those pharmaceuticals. But in all cases, they're starting from a simple molecule like this, doing a simple elimination, and then taking it on to a much more complicated molecular structure. Okay? That's how the other spelling. There it is. I knew I had it somewhere. Yeah. If you look at this structure, we actually have 2 different flavors, if you will, of beta carbon. We have beta 1s and we have beta 2s, right? If we eliminate one of the beta 1s, we get this product as a major product. If we eliminate at beta 2, we get this product but it's the minor product, okay? Why is this the major product? Okay, so you think it's due to kinetics? It's not. What does that have to do with it? That's right. It's all about thermodynamics here, okay, not kinetics. So it turns out that the beta 1s, when you eliminate one of the hydrogens, you get a trisubstituted alkene. And if you eliminate at beta 2, you get a disubstituted. And we know that the more substituents we have around an alkene, the more stable it is, right? So if I can stabilize the alkene, what's that going to do to my transition state? Is it going to lower it or raise it? It's going to lower it. And if I lower it, what's going to happen to the rate? That's right. So we end up with the more thermodynamically stable product, but it does lower the transition state. And so there is a rate component to it, okay? But it does have to do with the stability of the alkene. This is Zaitsev's rule. Basically, Saytzev's rule states that if you have more than one beta carbon, one type of beta carbon, the beta carbon with the fewest hydrogens is going to lose the hydrogen in the reaction. Okay? The carbon with the fewest hydrogens will lose it. Okay? So it's kind of a wealth argument, right? The carbon that's least wealthy in hydrogen is the one that gets taxed. Okay? If to put it in political terms. All right? So that's what's going to happen. All right? And so when we look here, we've got beta 1, and what kind of carbons are these? They're secondary, and what's beta 2? It's primary. And so this secondary carbon has to have fewer hydrogens, and you do the elimination. Now, it doesn't matter if you eliminate from this beta 1 or this beta 1, you get the same product. Okay? And so you should be able to predict which of the alkenes you're going to get as the major product. I do not expect you to be able to predict 75%, 25%, or anything like that. All I expect you to do is predict major and minor. Okay? And in this particular case, the major would be probably around 85, 90%. This beta carbon has 2 hydrogens, right? This beta carbon has 3. So you're going to lose from the beta 1s. Yep. That is Zaitsev's rule. Okay? And so basically what this means is this reaction is what's called regioselective. The region where that carbon-carbon double bond is going to be is selective. It is not specific. You will get a mixture, but that mixture sometimes is quite large, right? You can have 90, 95, 99% of the major and very little of the minor, but you will get both products. And if you look at the transition states, that's what explains all of this, right? So as we go through, in this particular case, this alkyl halide, it's tertiary. The reaction should go very well. We're going to use sodium hydroxide as the base because we can't do SN2 chemistry. We've got a beta 2 and 2 beta 1s, right? And so when we look at this, we know if we go through the beta 1, we're going to go through this transition state, which would give us a disubstituted alkene. If we eliminate at beta 2, right, we go through this transition state, which is a trisubstituted. It's a much more stable transition state, and this would be our major product, would be the trisubstituted alkene, okay? So the E2 reaction is regioselective. When you see a good base that can't function as a nucleophile and you've got an alkyl halide, label the beta carbons and ask yourself which one has the fewest hydrogens. That will give you the major product, okay? And then you can figure out the minor products by just looking at the other beta carbons, okay? Here's another example where we have this alkyl halide. Here we have 2 aromatic rings attached to it. We are using sodium methoxide as the base. We get 2 alkenes products out of this. We get the trans alkene, and we also get the cis alkene. Why is the trans alkene favored? That's right. So we want to have the big stuff as far away as possible, right? So this is known as stilbene, and this is known as trans stilbene. It's a solid at room temperature. This is cis-stilbene at room temperature. This is a liquid. So these actually have different physical states. We can separate them how? How would we separate these two? If one's a solid, one's a liquid. You could filter out, if you're lucky. But the liquid would still be kind of stuck on the solid somewhat. How else might we purify them? The vacuum thing? Okay. Okay. What techniques have you all done so far for purification? Have you done recrystallization yet? Yeah. So we've got a solid and a liquid. We could put them in a solution where the liquid would remain in solution and the solid would precipitate out, right? We could recrystallize the solid perhaps. So we could do that, or we could try to boil away the liquid. That's another possibility. Okay. So I want you all take a couple of minutes. What is the major alkene produced by elimination from the following? How do I approach this problem? Label the beta carbons? Okay. How would I label them? So here's my alpha carbon, right? So what would I label this one? I can label that beta, and what would I label this one? Beta 2 or beta prime, whatever you want to label them, I don't care, right? And I know from Zaitsev's rule I'm going to eliminate from which one here? That's right, from this beta, right? And so my product is going to be that. That's going to be my major product, right? How about for the second one? Let's see, I've got that. How many different beta carbons do I have? I've got 3. I've got beta. So I could have up to 3 different products. Which one of those is going to be the major product? Because it's only got 1 hydrogen. So the main product from that elimination, and I'm drawing kind of weird here, would be that, right? What would be the next most abundant? Beta double prime, and then the least abundant? Beta. That's right. So identify where your alkyl halide is in an E2 elimination, label the beta carbons, and then follow Zaitsev's rule. Okay? Follow that process and you'll be good. Don't follow that process, you won't be so good. Okay? Identify alpha, identify the betas, and follow Zaitsev's rule. Okay? At least for now. Let's talk a little bit about E1 elimination. E1 elimination is going to mirror a lot of what we talked about for SN1, right? The rate of the reaction is unimolecular. It does not matter the concentration of the base. It only matters what the concentration of the alkyl halide is. Okay? So, the rate is going to be proportional to some rate constant K times the alkyl halide concentration. So if Gabriella came into lab and she wanted to do an E1 elimination, and she said, I got to get to lunch real quick, so I'm going to double the concentration of the base, she's going to be there just as long as if she hadn't. But being the smart person that she is, she walks in, she knows she has to double the concentration of the alkyl halide, she's going to double her rate, and she's going to be able to go to lunch on time, right? So that's how that works, just like an SN1 reaction. So what is the intermediate in an E1 reaction? It is a carbocation. That is exactly right. So the leaving group leaves. We end up with a carbocation, right? And so anything that can stabilize the carbocation is going to do what to this step? Speed it up or slow it down? Speed it up, right? And that's why we're seeing tertiary here, right? Tertiary works really well. We get a tertiary carbocation. And now the base comes in and abstracts the hydrogen, and you end up generating the alkene. Now, we just did an experiment where we took tert-butyl bromide and tert-butyl chloride, but I told you these were SN1 reactions, not E1 reactions, right? What can you look for on your video to see whether or not we were doing E1 or SN1? Temperature? Okay, what temperature did we run this at? Room temperature. So would you call that hot? No. So that's going to favor substitution. What else could you have looked for? Does anybody know what the physical state of this molecule is? Is that a solid, a liquid, or a gas? Pardon? That's pretty low molecular weight. Maybe, well, it's definitely not solid. Does it have a high molecular weight? So is it mostly likely going to be a liquid or a gas? It's most likely going to be a gas. Did anybody see a lot of bubbling going on in that reaction where it was releasing a gas? No. Now, if you look really carefully at your video, you might see a few little bubbles. But who knows? That could have been from me shaking, right? So, but if it had been an elimination, we would have generated a lot of gas, and the pressure in the bottle would have actually increased, and if I tried to open it up, you'd hear it whoosh, and that didn't happen. That doesn't happen, okay? And so how could we have gotten that reaction to go through elimination as opposed to substitution? We could have heated it up. That's exactly right. Okay, and so the difference here is, of course, water isn't functioning as a nucleophile, it's functioning as a base, and we go through an elimination process. Okay? The reaction diagram looks almost identical to an SN1, right, except the products are different. You start off with your alkyl halide, you go through the first transition state where the halogen carbon bond is breaking. We're starting to form a carbocation. We get to a carbocation intermediate that then undergoes a second a small transition state, right? Because the water has to come in and abstract this hydrogen. That's a transition state, but it's small, and you go down to the final product, right? And so this transition state, I think you all will agree, has a much higher hill to climb than this one, and so this is what controls the rate of the reaction, right? It's always the slowest step that controls the rate of the reaction, and so it's the formation of the carbocation that's the rate determining step, okay? And so you'll see the trend that as you increase substitution, you're going to increase the rate of E1, just like you increase carbocation stability. That's not too surprising. So we know that tertiary alkyl halides can do E1 elimination. They can also do E2 elimination. Primary alkyl halides cannot do E1 elimination, but they can do E2 elimination. Secondary, where are they going to be? They're going to be somewhere in the middle. Okay? Secondary alkyl halides are going to be the bane of your existence in these chapters because they can do E1, they can do E2, they can do SN1, and they can do SN2. So you're going to need to know your conditions. If I want a secondary alkyl halide to do substitution chemistry as SN2, I need a good nucleophile, I need a polar aprotic solvent, and I need a good leaving group. If I want that secondary alkyl halide to do elimination chemistry, I'm going to use a poor nucleophile, a good base but a poor nucleophile, right? So you need to kind of practice those, especially with the secondaries. They're going to be the tough one, okay? E1 also follows Zaitsev's rule. That's kind of convenient. You don't have to memorize two different versions of Zaitsev's rule, right? So here we've got our alpha carbon. We've got two different beta carbons. Leaving group leaves, we get a carbocation. The tertiary or trisubstituted alkene, I should say, is the major product. Okay? So it doesn't matter whether you're going through E1 or E2, follow Zaitsev's rule for the time being. Later on, especially when we get into 256, we'll learn where there are exceptions to Zaitsev's rule. Okay? But for right now, we're going to follow Zaitsev's rule pretty religiously. Okay? So the difference, of course, between an SN1 and an E1 reaction is how the base is functioning. Right? If the base attacks the carbocation, it's a nucleophile and you get substitution. If the base attacks a hydrogen, it functions only as a base and you get elimination. Okay? E1 and SN1 always compete. And it turns out that SN1 reactions and E1 reactions, chemists don't like to use them because of this competing pathway. Unless you have a situation where you can really control whether it's going to go through elimination or substitution, you rarely want to do E1 and E2. E1 and SN1. Okay? And so we say that these are much less useful than the SN2 and E2 reactions. All the examples I showed you from the pharmaceutical side of things, right? They were using SN2 and E2 type eliminations and substitution reactions because they're well controlled. Okay? Now we know that in the E2 reaction, we have to have the hydrogen and the halogen trans to one another, as you've been calling it up to this point, but actually that's called antiperiplanar. Okay, they're in, the hydrogen and the halogen are in the same plane of the board right now, right? But they are anti to one another, if you will. So if you looked at the Newman projection down this carbon-carbon bond, you would see the hydrogen and the halogen in an anti-configuration, or conformation, excuse me. Okay? But they lie in the plane of the board, and so that's where we get antiperiplanar. Okay? We can also have the hydrogen and the halogen being syn-periplanar. But this relationship cannot undergo elimination. Why? In an E2 reaction. But why? Why should that matter? It does, but why? So as the base comes in, right, and plucks off this hydrogen, where do these electrons go? They form the carbon-carbon bond, but they're kind of coming in from the back side of this, right, and kicking out the leaving group. That's right. So if I have a base coming in here, these electrons would have to come in from the same face as this, and that's just not lined up right for that chemistry to occur. Also think about it. The base has a lone pair of electrons, right? What does X have around it that's not shown? Lone pairs of electrons. So is the base going to want to approach from this face? You're going to get lone pair repulsion. That's right. So you got to keep thinking about those types of things. Okay? So you can see quite clearly here, these two electron-rich groups are far apart, so that's a good thing, whereas here they are much closer together, and that is a bad thing. Okay? Now, if you think about chlorocyclohexane, we can have a situation where the chlorine is equatorial or the chlorine is axial. And we know that this is more stable, right, than this, because we want the big groups always to be equatorial, right? However, this can't undergo elimination. None of these hydrogens on the beta carbon are antiperiplanar to that chlorine. It's the least stable chair conformation that is responsible for the elimination. And when that chlorine is axial, notice these two hydrogens are how with respect to the chlorine? Antiperiplanar. Build a model tonight, and you will see that none of the hydrogens are antiperiplanar to that chlorine when chlorine is equatorial. But it is here. So sometimes the least stable chair conformation is responsible for the chemistry that we observe in these types of things. All right. That's all I'm going to talk about for today. We will have an inverted lecture on Friday. Your exam redos are due today by 5. If you've got it now, you can turn it in. If you didn't do it, make sure I get the exam back.